Kaplan. I'm an engineer on the Avalanche Bridge team at Ava Labs. We're going to be talking about how we leverage Intel SGX technology within the blockchain space, how we used it to build the Avalanche Bridge, and what we can do in the future. So to start off, what is SGX? SGX is Intel's trusted execution environment solution. So it's hardware that enables secure remote computation. So I'm not sure if you're all familiar with the problem, but basically it's how you are able to ensure that a remote party is running a program correctly. When you access a remote client or when you are sending a request to a remote client, that client can handle the request however they would like to, and you're trusting them to do so honestly and correctly. But obviously that becomes a problem when you're talking about high-value applications, and there's a couple different approaches that the space has taken to try to address that. One is software-based, which is when you get into blockchains and distributed ledger technology, and the other is hardware-based. What Intel did is basically isolate the processor from everything else. It's on its own chip running in an isolated, secure environment that they call an enclave. And it provides this tamper-proof confidential execution. So you can get proof, a remote party can get proof that a program is running correctly on a valid Intel SGX chip without needing to replicate that execution across all of the nodes in a blockchain. So there's a couple different ways that Intel leverages this, or they were envisioning use cases would use SGX. One is a client enclave where all of us with, say, on our smartphones are running SGX. Then a remote party that wrote software is able to tell and prove that we are running their software correctly. So the most common use case for this is digital rights management. And the way that would work, say Spotify could verify that all of its users have the proper access to be able to, or copyright to be able to listen to a certain file or the like. Flipping that on its head, though, is when you'd put the enclave on the server side, and that's the model that we've followed at Ava Labs. So the way that works is that all of the clients are communicating with one backend that could be running any arbitrary application, but you as a client are actually able to prove that the backend is behaving correctly. So that's a super powerful concept. When you think of like Facebook, for instance, you could get proof that they are not selling your data, that they are storing it correctly, that it's encrypted, and that it's not being leaked to other parties. So you can think of really any general use case of just being able to verify that the server you're talking to on the other end of that website is behaving correctly. So then we get into SGX and blockchains. I actually got connected with Ava Labs through Goon back at Cornell when I was taking his blockchain course, and that is when he introduced me to SGX. And he, from the start, was basically very bullish on the shared ethos between SGX and the blockchain space as a whole. Both are trying to reduce the level of trust needed in systems so that the end users don't need to trust, frankly, that the party that they're connecting to is behaving maliciously or anything like that. So this completely changes the Byzantine fault tolerance model within a distributed network. In blockchains, you have all of these independent nodes, and you trust that a certain percentage of them are behaving honestly. So obviously, you can get a 51% attack in Bitcoin or any proof-of-work network. In proof-of-stake networks, it's slightly different dynamics, but you're still trusting that the majority of the stake is behaving honestly. And even if a certain smaller percentage of that is acting maliciously, it won't affect the correctness of the network as a whole. When you apply SGX to that problem, you end up in a whole different world because you can get proof that each individual node is running correctly. So now you have a totally different dynamic of the communication between nodes to nodes or user to node, because you can actually prove that that single node is running the program correctly rather than needing to replicate that execution across all of the nodes in the blockchain network. Some possible use cases we have listed here. Off-chain smart contracts. When you think of smart contracts, really what they are is the execution of a set program that's replicated across all of the nodes in the blockchain. So you get the security of the blockchain, meaning that if 51% of those nodes are honest, you're guaranteed that correct execution of the program. But when you move that into an enclave, you don't need to replicate it across all the nodes in the network. You can get proof that a single node ran your program correctly. And then secure key generation and payment channels. For the OGs here, I think T-Chain was the original SGX application that Goon published a paper on many years ago, even before Avalanche. And it basically describes how you could make the Lightning Network using SGX. And he can call it T-Chain. Yeah, so then how we applied SGX at Ava Labs, the first application that launched was the Avalanche Bridge. So just a quick background on what bridges are. I'm assuming most of you here in the room know this already, but bridges act as an intermediary for moving between two different blockchains. They're necessary to increase liquidity flow and access to DeFi applications. So if you have your link on Ethereum and you want to leverage it and stake it in Penguin, obviously you're not able to do so directly because Penguin lives on the Avalanche network and is totally independent of Ethereum. But with bridges, you're able to move your link over to the Ethereum network and then use it in all of the applications there. So there are two common models for bridges. One is the lock and mint model. So you have your link on Ethereum and you send it to the bridge on Ethereum, and the bridge then mints you some wrapped token, which is basically an IOU on Avalanche saying this address holds, you can call it whatever you'd like. With the way we denote wrapped assets in the Avalanche Bridge is by putting .e on the end of it. So you mint the .e token to the same address that sent you the token on Ethereum. The other model is the pooling model, which has some different properties, but the way it works is that someone initializes two pools of equivalent assets on two different chains. So you have your existing USDT on Ethereum and your existing USDT.E on Avalanche. You put them into a pool on both sides, and then users are able to deposit into the pool on one side, and they earn the right to withdraw from the pool on the other side. This is really nice because you don't necessarily need to have that synthetic or wrapped asset. If you have the native asset, USDT, on both chains, you could create a pool directly between those two, but it has limitations because you need to keep those pools maintained. And if you have a new, really fast blockchain based on a novel, sorry, what? If you have a new fast blockchain based on a fast consensus protocol and you want all of your users flowing into it, that pool will empty out and the ETH pool fills up. And that obviously has significant limitations there. Only a certain amount of funds can flow in either direction. Yeah, so we thought the bridge was this bridge problem was a perfect candidate for SGX because the communication between the two chains is not trusted. So there are Ethereum miners validating the Ethereum network. There are Avalanche Go nodes validating the Avalanche network. But the communication between the two is totally independent of each. Independent in terms of the trust. You don't have the Avalanche Go nodes saying, yes, this transaction is a valid Ethereum transaction. You don't have the Ethereum nodes validating the Avalanche network. So how do you know, how does one network know that a transaction actually did occur on the opposite chain is the crux of the problem. Yeah, so that brings us into the Avalanche Bridge. So it leverages SGX to provide fast, secure, and inexpensive transfers between Ethereum and Avalanche. The real, I think, value prop of the bridge is the best user experience on the market. I put a little graphic of the UI up there, but we use the same wallet on both blockchains. So you have your MetaMask on Ethereum. When you transfer it over the bridge, it's still within that same MetaMask wallet. That's a really nice property because it's super intuitive for users. It's also a really nice property because it makes it entirely transparent where those funds are going. Those funds stayed within the same wallet as they cross the network. It's not as if you can use it to send funds to anyone else or do any type of shady activities such as money laundering or the like. The operator doesn't control any of the funds in the bridge. That's obviously a very nice trustless property. and the operations of the bridge itself are moved off-chain from a smart contract into the enclave using that kind of off-chain smart contract model I discussed earlier. So the architecture of the bridge, there is one SGX enclave and 4 what we call wardens. The wardens are the nodes validating the cross-chain transfers. So I mentioned how that's the crux of the problem is how do you trust that one transaction was actually committed on the first chain. And we do so by relying on 4 independent nodes run by 4 different companies to inform the enclave of such. There's no publicly accessible APIs, which is another nice property. We don't have any scaling or networking issues because the bridge sits entirely in between the 2 blockchains and is easily able to process all of the transactions. It follows the lock and mint model that I discussed earlier. So then that really leaves the wardens. What do the wardens do? They store secret shares. So the enclave generates a master secret where it derives all of its keys and wallets from. That's obviously the most confidential information in the bridge. So what the enclave does is that it uses Shamir secret sharing to split that share into 4 different parts, or however many wardens there are, and shares one piece of that secret with each of the wardens. So the wardens then store that share. They perform remote attestation of the enclave. I didn't touch upon that in too much detail earlier, but remote attestation is the protocol in SGX where a remote party is able to verify that the code is running correctly in a valid enclave. So you can get proof that those secrets are, the wardens get proof that those secrets are safe and only given to the correct version of the enclave code. The code that's loaded into the enclave affects the identity of the enclave itself. And when you perform attestation, you're able to see you get proof of the enclave identity. So you can prove that a specific version of the source code is running within the enclave. And then the wardens finally report the unprocessed transactions that they've seen to the enclave. And the enclave only acts on those transactions once 3 or 4 wardens have actually reported that same exact transaction to it. So that's how we kind of distribute the trust there. So when you cross the bridge, like I said, it's presented in a really nice UI, but I just want to break down what's actually happening behind the scenes a bit more. So the user initiates a transfer across the bridge by sending a transaction on Ethereum. That transaction is transferring whatever ERC20 token they're moving over to Avalanche to the wallet controlled solely by the enclave. The wardens are then indexing the blockchain and looking for transactions that are being sent to the enclave address. So the wardens see those blocks being produced. Once it reaches the required number of confirmations on Ethereum, they index that as an unprocessed transaction. And then the wardens all relay into the enclave which transactions are unprocessed. Once 3 or 4 wardens all inform the enclave of the same exact transaction, the SGX app mints the wrapped funds. So there's one wrapped ERC20 token for each native ERC20 on Ethereum that we support. And then once that transaction gets broadcasted out back through the wardens, the users have their funds on Avalanche. Yeah, so the benefits of this, it's intuitive, low cost, and secure. There's no smart contract interaction on the Ethereum side, which really saves on all of the gas cost for the Ethereum transactions being sent by the users. And it's secure because no party ever has access to the funds crossing the bridge. So one set of interesting technical problems we faced when developing the bridge was how to design the fee mechanism to cross it. So we only support ERC20 tokens moving across, but in order for the enclave to be able to send transactions on Avalanche or on Ethereum, they need to pay the transaction fee in native ETH and native AVAX. And because of that, we need to be able to know the current price of each of the assets in order to charge the correct amount of the ERC20 to compensate for the cost that the enclave is paying up front. And obviously, we didn't want to just have any centralized price feed that's feeding the bridge because it could be manipulated in order to either raise or lower the fees for a given transaction. So what we did was leverage Chainlink's price oracles. Chainlink as I'm sure you all know, is an Oracle solution on-chain. We are off-chain in the enclave, but we actually pull their data from on-chain. So each of the warden looks at the current state of the Chainlink smart contracts and uses that as its decentralized API as the source of price, and then relays that price into the enclave. And that way the enclave is able to know the price of each of the assets and the value of each of the assets being transferred. If the value of the assets being transferred is above a configurable threshold, you get an AVAX airdrop, which is another nice UX feature on the bridge for sure, because anyone coming into the Avalanche ecosystem for the first time from Ethereum probably didn't have AVAX to be able to send a transaction and cover the gas cost. So being able to give them an airdrop for moving their funds over to Avalanche really kickstarts their entry point into the Avalanche ecosystem. Yeah, so we had a pretty good gut feeling that the bridge was going to have demand and really enable people to flow into Avalanche like they weren't able to before, but we did not have a good idea as to the scale of which it would be, it would catch on really quickly. So on the right there, you can see the graph of the total value locked in the bridge over time, which was super incredible to see. We launched at the very end of last July, at the start of April, so that can starts from zero there and got up to over 7 billion in November, December, which was absolutely incredible. For the first 4 months post-launch, we had over $7 billion locked in the bridge. That doesn't even account for the amount being transferred back and forth. That's only the current value locked at that point in time. And yeah, we had over 245,000 transfers from ETH to Avalanche and 110,000 back, so over double are entering rather than leaving. There are a lot of interesting possible attacks on different bridges. I'm sure you all have seen the recent exploits on different bridges in the blockchain ecosystem. These are a few that we were particularly concerned about when designing the bridge and how we made sure that the design accounted for them. So what happens if you have a warden that's lying? If the warden wants to push through a bad transaction, it can report to the enclave that it sent the bridge $1 million and try to get the enclave to then mint them that money. But we follow this K of N model where at least K wardens need to all report the same exact transaction, which distributes the trust a bit. There are more traditional Web 2 type of attacks, DNS or SSL exploits, and that could potentially corrupt the communication from the enclave to the warden. But we leverage HMAC signatures so that the enclave and the wardens are able to verify all of the messages end to end. Another possible attack vector is unauthorized access to the enclave, the machine the enclave is running on. But like I said earlier, SGX really solves this problem for us. Even if you have access to the machine where the bridge is running, you don't have access to the enclave, and you have no access to be able to see the state of the enclave, its memory, affect its execution in any way other than possibly unplugging the machine or turning off, killing the process. So we like to say that the operator of the bridge, Avalabs in this case, is trusted for the short-term availability of the enclave, because the operator certainly has the ability to just turn it off and disappear. But if that were to happen, the other 3 wardens are perfectly capable and able to start their own enclave and continue the execution of the bridge without any interaction with any party. In this case, Avalabs it would be. Yeah, and that's really a core property of that. You're not trusting a single party, even for the availability of the bridge, because the other 3 parties would be able to continue on the operation without Avalabs. Yeah, and malicious bridge operator would be the last one to note here. So what if Avalabs pushes a bad commit to the bridge repo? And the way that this is solved for in our model is that the wardens all perform attestation of the enclave every time the enclave restarts. So the wardens are verifying not only that the enclave is running in a valid SGX enclave, but also the version of the source code that it is running on. So the wardens have access to the source, they're able to see all of the commits, and they actually approve every new version of the enclave by adding the hash of the code into their allowed enclave versions, basically. So every time we do an update, we ask the independent parties to approve this new version of the enclave, and they are able to review the code there. Yeah, future directions that we're moving in. Multi-network support, so it's not limited to just EVM to EVM transfers. It's the only thing that's live today, but this model, since I mentioned it's like off-chain smart contract execution, but the smart contract isn't just a Solidity code, it's just arbitrary C++ code, so you can do whatever you'd like with it. You can pass arbitrary data across chains, and most exciting, we can support BTC transfers, which we will be soon releasing. I think Nick just announced that over at the mainnet stage. So it's something we've been working on the past few months. It's an entirely different problem in terms of validating that the transfers actually occurred, since Bitcoin uses a UTXO model versus the account model of the EVM. There are a lot of technical intricacies there that I won't get into, but we are able to take them on because of this off-chain SGX environment. Yeah, so that was all I had, but happy to answer any of the questions that you guys have also. Connie?
Yeah. How do you foresee the bridge model and the kind of ease of use that it provides extending to BTC versus the other BTC bridges that are out there?
Yeah, great question. So our model is really nice in that it encapsulates all of the smart contract calls that would occur in other bridge models off-chain. So when you send a token to the bridge address, you are interacting with the smart contract of the enclave. Obviously, Bitcoin doesn't have smart contracts, so it'd be very difficult to launch that type of behavior on-chain in Bitcoin. But when it's easy enough to send a transfer to a specific Bitcoin address, and if that address is the one owned by the enclave, then the enclave can process that transfer as if it were a smart contract living on Bitcoin. So that allows us to really make the user experience far more streamlined than other bridges.
That's really cool, very interesting. How does the enclave get access to data outside of the enclave? So database queries, stuff like that. I guess is it all sent together as
Yeah, that's a very interesting question, and it is a super interesting problem to try to get around. So in our model, the enclave is totally stateless. It has no database. The only way that it's able to get information about the outside world is through the wardens. And it has, there's two ways that it can get information from the wardens. One is for specific specific values that it should be expecting. So the transfers that occurred that it hasn't yet processed. The wardens all have their own MySQL databases that they're indexing the on-chain data into. And so when it queries the wardens for that, the wardens are looking that up in their own databases. But for the specific transaction information, that needs to match exactly across at least 3 or 4 wardens for the bridge to act on it. Other data points don't necessarily line up exactly from each warden because they each have an individual or an independent view of the network. So when I was mentioning we use the Chainlink price feeds, and we also ask the wardens for the current gas prices on each network in order to approximate the transaction fees. Those values that one warden might report 44 Gwei, one warden might report 45 Gwei, and both are being totally honest. They just have slightly different views of the network. So for those types of queries, the enclave, typically what we've done uses the median result so that you need, in this case, at least 2 wardens to affect the gas price there. Yeah, so all of the information about the outside world is pulled in through the wardens, and then how the enclave parses that information depends on whether or not it should be exactly the same from all truthful wardens or not.
I was just gonna ask subnets. Do you have any plan to extend this bridge to subnets? Like, can it be used by subnets in the future?
Yeah, we've had many discussions about this internally, actually. The current plan for the SGX bridging technology is to only apply it to high-value bridges. And we've seen this actually for high-value assets that we really expect a lot of liquidity for. We've seen this kind of at the tail end of the supported asset list. If you bridge over those tokens, the bridge is perfectly able to support them, except there's not a lot of liquidity for them on Avalanche. So you might bridge a token and then you want to use it on Pangolin or something, but then there's insufficient liquidity and you can't trade it and you're not really earning rewards on it, so it's not a great user experience. So we don't want to use it for those lower liquid assets. But if there's a particularly popular subnet, then that's something we would be interested in. And we're also looking at other ways to support subnet to subnet transfers and interoperability between those two subnets. We just want to make sure we're applying this specific technology in the right cases.
Thank you. So from your slide where you describe the attacks, I suppose one attack would be that the majority of the wordings get compromised, right? So if that's, is that number that you showed there, 3 out of 4, a reasonable balance that you found between, like making it more decentralized and security, or was it a limitation from Samir's secret sharing, or why 3 out of 4?
Yeah, great question. We're actually going to be increasing that number to 5 of 7 for the Bitcoin bridge and for the existing bridge in the near future. We'd definitely like to see it increase into the double digits. It's something that was more of just we felt comfortable launching with at the start. That's for reputable organizations. There are bridges that rely on fewer than 4 relayers or communications between the two chains. So definitely something that the more you get, the more security, most theoretically secure the bridges. There is overhead of, okay, we need more partners. We need more partners to update to the latest versions. We need more partners to maintain their deployments. But it's definitely a number we want to see increase, and we are increasing it to be 5 of 7 in the near future.
So I've seen a lot of material out there that SGX might not be as secure as we think it is. Does the bridge kind of take that into account? And why do the possible existing attacks work against the bridge or do not work against the bridge?
Yeah, so there definitely have been a few SGX exploits. And the kind of saving grace of most of them is that you actually need physical access, or at least root access, to the machine that the code is running on in order to try to execute those exploits. So within our model, the SGX security is kind of stacked on top of traditional Web 2 security. And if, say SGX was completely broken, it was all a scam, and it's actually just running on a normal laptop somewhere that someone has access to, we are limited to the fact that it would only be the person running that laptop who's able to perform that attack. And that's a very, very nice property to be kind of stacked on top of our security model as we expect it to and know it to work in terms of the SGX exploits. So if there was a 0-day SGX exploit, rather than anyone being able to sign and send a transaction to a blockchain that exploits a smart contract bug with complex smart contracts we've seen on other bridges, only in our case Avalabs would have the capability of actually performing that exploit against our bridge. And that's not a model we like to kind of push out publicly too much, because it's like, what if everything is broken? Like, yeah, then you have to trust Avalabs. But everything's not broken, fortunately. It's a technology that's gaining more and more maturity every day, and that Intel is, and frankly other reputable software and hardware companies are working on. So we expect it to be working correctly, and we expect any exploits or potential vulnerabilities to be patched. But if there were a catastrophic failure in SGX, it would be limited to just Avalabs who is able to exploit that. Yeah, all great questions though, thank you. One more? Yeah.
Got it. I guess this means you could apply smart contracts to any blockchain network, right? Like you just smack a little
Yeah, the use cases are really endless because it's not truly a smart contract, but it's verifiable execution. And you can get a lot of the properties that you're looking for in smart contracts in terms of correct and honest execution, confidentiality, privacy of all of your data. You can get all of those properties of smart contracts within applications running within SGX. So the applications there are really endless and not just limited to the blockchain space.
Cool.
Thanks, everyone.